The first example we have is using TCGA embeddings to model cancer survival. The TCGA, or the Cancer Genome Atlas, is a highly curated, harmonized pan-cancer dataset spanning 33 cancer types with multiple harmonized data modalities and survival outcomes. This demo is derived from our recently accepted paper, Multimodal Cancer Modeling in the Age of Foundation Model Embeddings. Please give the paper a read if you're interested in our in-depth analyses. In this demo, for simplicity, we focus on a single cancer type, lung adenocarcinoma, as part of the TCGA LUAD project. Just as in our original paper, we use four data modalities: tabular clinical data, RNA-seq gene expression, histology images, and pathology reports. The benefit of the AI Commons is that all the necessary pre-processing and embedding has already been done. These embeddings are ready for downstream modeling. In this demo, we'll show that utilizing classical linear models over embeddings can additively predict survival as we add more data modalities. Briefly, our overall steps are as follows. First, we pull the TCGA LUAD embeddings from the AI Commons. We next pull the associated metadata from the GDC, the Genomic Data Commons, where the source TCGA data lives. After merging the embeddings and the metadata, we can run our experiments. Specifically, we train unimodal survival models before doing multimodal fusion, where we ultimately show that our full multimodal model outperforms any unimodal model. I've pre-run all the cells of this demo notebook for this video, but I'll go over them very briefly. First, we install and import some dependencies. Next, we do the very critical component of pulling the embeddings from the AI Commons embedding service. This is very similar to pulling data for any other Gen3 Commons, where you start with a manifest file, and specifically here we have three manifest files, one for each data modality of embeddings that we have in the Commons. So that's gene expression, histology slides, and pathology report text. After we pull all the metadata, after we pull all the embeddings, we can then pull the metadata from the GDC. One of the cool things about the AI tools that are mentioned in other videos is that some of them are enabled as MCP servers as well. Meaning, if we want to use, for example, the GDC cohort copilot to assist us in pulling this metadata for the TCGA LUAD samples, we can do so using the MCP endpoint. So here's that MCP endpoint where the tool is named generate filter. This can be used by an LLM as in any other MCP tool, or in our case, we can also use it manually here in this notebook. We can use this helper function that executes the query using the cohort cofilter, copilot MCP endpoint, and we can specify that we want either the diagnostic slide SVS files, the RNA-seq TSV files, or the pathology report PDFs. And here are those filters describing exactly what we had wanted in those prompts. So here's the histology filter, here's the RNA-seq filter, and then this last one is for the pathology report filter. We can execute those queries using the GDC API, just as you would in any other case, and we can grab all the metadata for these TCGA LUAD samples. Next, we want to join the metadata that we've pulled with the embeddings that we've pulled, and that's what this section is doing here. And lastly, we want to prepare our experiments. So we do a train test split of 80% to 20% of our data. And then we construct this one helper function that will run all of our experiments for us. Very briefly here, if our input data needs to be standardized, as in the embeddings, we can do so. We can apply z-scoring here. If we want to do PCA reduction, because, for example, some of the embeddings are very high dimensional, we can also do that here. Then we train our actual Cox proportional hazard survival model over the transformed data. And finally, we predict our risk scores and evaluate the performance of our model using the concordance index, otherwise known as the C index. Very briefly, the C index is a measure of how well a model predicts survival, where a 0 means very, very poor performance, and a 1 means perfect performance. So the closer you are to 1 on the C index, the better is the model. Next, we train all of our unimodal models. So again, over our tabular demographic features, our expression, histology, and text embeddings. Then we do multimodal fusion over those four modalities. And if we evaluate our model again by the C index, we find that all of our unimodal models are not cracking this C index of zero point 0.7, but our multimodal model does break that barrier and significantly outperforms all of our unimodal models. So ultimately, the takeaway is that these embeddings provided by the AI Commons enable really rapid and quick development of downstream analyses and models. For example, in this case, survival modeling over the TCGA.